Hello everyone, and welcome to Handmade Hero, the show where we code a complete game live on stream. We are going to play with the lighting a bit today and see if we can't make some progress on, just something that we like, is I guess to say about it. We're not trying to do anything fancy here. We're just trying to come up with something that spreads light around the scene in a way that we feel like makes some sense, right? And that's really about it. So I don't know, again, if we're on the right path. We may have to substantially change some things, but we have a nice path working right now where we can essentially generate some lighting information that we can then iterate on, and we can play around with what we're storing and how and what sort of iteration passes we're doing on it without having to redo everything. So we're in a reasonable spot, I think, to experiment and hopefully find something good. Again, it's one of those things where you never really know when you head down, if you don't have a particular algorithm in mind. When you head into something experimenting, you have no idea what you're going to find when you do it. However, I was somewhat emboldened by the fact that our depth peel renderer ended up working so charmingly. I kind of feel like, that maybe led me to being a little more foolhardy than I would normally be. So we're kind of going for broke here with the lighting. And we're just playing around with a lot more lighting than probably ever should have been warranted on Handmade Hero, since this is an educational stream and we're not trying to, come up with any kind of new algorithms or anything like that. But, sometimes you just get carried away. So anyway, where we left off last time is we have some lighting visualizations here, and we can sort of look at a couple of those. But what we essentially did was we've got our lighting rendering so that we have a few different planes of information that we can look at. We have the surface reflectance color, which is this. We've got the inbound lighting. We've got this right here is a term we were analyzing that we don't really care about talking about right now. We have the surface normals, which we were showing here. And essentially what we're trying to do is iterate over these in some way as to produce some good lighting bounce around the scene. Now what we determined, and I think it's pretty reasonable, what we saw happening here is that when we looked at what was happening in the scene, unfortunately our scenes just tend to have a lot of, they're just basically a flat ground with some slight height differential. That's really all we do, right? And although on the interiors we'll probably have some dungeon wall kind of stuff, we just don't have a lot of reflectors. So one of the problems we were seeing is that if we do a system that relies heavily on transmission angle, we're going to be in trouble because we just don't have a good coherent way of figuring out how that's really going to work. We would probably have to add a synthetic ceiling into the scene in order to sort of have there be something that reflects light back downwards. And again, that starts to get into things that complicate the renderer quite a bit, because figuring out where that ceiling is would essentially require us rendering one more layer above the layer we're currently on. And while we could try to do something like that, and while we do get that for the layers below us, because we do have this layer on top, right? I'm not sure what we can really do there reliably, and maybe I'm dismissing this out of hand. I'm not sure, but I definitely feel like there's a big question mark hanging there about what we would do in terms of getting reflectors that would push light back downward. So I don't know. That's kind of one of those things where I really don't have a good solution to that. Part of me is tempted to try and figure out a way to put in the upper ceiling, which would be basically a skylight in the outer world, and it would be the dungeon ceiling inside sort of the dungeon areas or whatever else when somebody's indoors. But, you can see why I'm a little hesitant to do that, because I'm just not sure how to get that in there in a reliable way. I really just don't know. And it would add a certain level of complexity as well, because in order to do that, we would have to sort of render one more depth peel above the current depth peel, right? So I don't know. But at the same time, is it that hard to do? Not really, since we already have a depth peel renderer. If all we wanted to do was produce where that top level was, it's not the end of the world, because what we could do, I suppose, is just turn off the front clip plane. Well, turn it off is not feasible, but push it back, right? Push back the front clip plane. And render into another buffer the furthest away depth layer that is above the depth we have in the highest depth peel, right? So we'd basically be taking the, like, in fact, what we're looking at right here, right? This scene, what we're looking at. We would take the depth of everything in this scene. We would render the next layer on top of that. And we would then take all of those, and those would be, you know, our downward reflectors. Those would be our ceiling, right? So that's, you know, that's what we're looking at. Unfortunately, I don't really know how sane of an idea that is. And that's the problem whenever you're playing around with new rendering techniques, is you never really know what's going to work ahead of time. You're really in a trial and error land. You can use your best judgment, but your best judgment is not always good enough. And you may end up deciding not to go down a path that actually would have turned out to be fruitful, and later on you'll read about somebody who did follow it through and arrived at a great algorithm, and you're kicking yourself for going, I could have done something better there. And other times you'll go down a path that just turns out to be completely useless, and you've wasted a bunch of time on it. So there's plenty of risk in both directions, and it's just tough, right? There's no other way to say it. It is a difficult situation, but that's just the nature of the beast. So you got to just get over it and plow forward. So the question is, what do we do now? Well, we've got two possibilities, right? One is we try to push the reflector stuff forward, and the other is we try to do something a little more localized. So one of the things that is true about the way this lighting was working is that if we were to turn off the part of this that really deals with angles, which we did try on the stream before, we have this facing direction term here. And if we wanted to turn off this facing direction term so that it doesn't attenuate based on facing direction, and instead we just attenuate based on fall off, then one of the things we can see, right, is we can see the light does spread around in a somewhat interesting way, right? And we do have some sampling artifacts. Those are due to the way that we are downsampling, which I think we can fix. And that's just, you see how the light kind of shrinks and grows? That shrinking and growing of the light is just an artifact of that particular problem, right? Of that sort of, what's the word I'm looking for? That's basically just an artifact of the degree to which the sampling lines up on the square boundaries as it gets downsampled, right? And so we can fix some of that by improving our downsampling. So that shrinking and growing doesn't concern me too much. We can at least pretend for now that we can fix it, because I'm pretty sure we can. That's not the biggest problem. The biggest problem that we would have here is the shadowing of these things. But if you just look at how this light is playing around, right, you could imagine if we go ahead and did some lighting on this, maybe we could make this work just by itself and leave the facing direction stuff out of the equation for now, right? It's possible. So maybe add some shadowing in here, and then use it to do our lighting. And who knows, maybe that's sufficient, right? We don't really know. So what I'm interested to do is, I think what I'd like to do today, just as a first step, is before we go any further, I'd like to go in and add the final step of producing an actual output image that grabs the lighting data from the lighting information that we have produced, and then goes ahead and renders that image out to the screen so we can see what we would be looking at if we use this light propagation to produce our final image. That way we'll know whether this is close enough or whether we need to really worry about that basic facing direction information. Because it may be that the normals just aren't that interesting in our particular game, and we don't need to worry about them when we're convecting the light around, and instead what we should do is just transport the light around as if there were no facing directions. And then when we're done, use the facing directions to attenuate the light only when we go to do our final sort of gather, if you will, when we just take it and look at what that actually looks like, right? So I don't know. There's like a thought for you. It may be really stupid and crappy thought, but we'll play around with it and see how it goes. So what I'm going to do is just introduce our final shader, which in theory I think would be the last one we have, because you know, unless we decide to do some special effects in the future, we might have some shaders that do special effects. But what that is our final resolve now needs to get a little bit more fancy. And what we can probably do is not actually write a whole new shader. What we can probably do is just tack this on to our one of our final ones. So if you take a look at how our program is currently working, what you can see is that we do this final stretch at the end, for example, right? And we also do this peel composite step at the end. So either one of these steps could grab the lighting information and use it. So what I might suggest is this peel composite, which kind of is the thing that right now takes all of the depth peels and smushes them together. What we could do is take that peel composite, and instead of treating it as something that's just designed to composite the multiple samples of depth together, we could have that compute the lighting at the same time. Now, there's a number of benefits of doing this. One is that this gives us the freedom to actually apply the lighting differently depending on which depth you're at. If we want to do that, we can, and that's kind of powerful because it means that we can spend more processor time in the GPU to get better lighting results that take into account the depth of the thing that we're lighting at the time that we actually composite it. That seems like a positive to me. The other thing that I like about that is that since we're already in there and we've pulled in all the data, we can now just pull in the extra lighting data as well, and at that point we're not doing a whole nother pass of grabbing everything in to go ahead and compute that lighting. We're just pulling everything in once, we do it, and we put it forth, and we're done. And so I think that is probably the more preferable way to approach the problem, is to stuff everything into the peel composite and do it there. So with that in mind, I think what I'm going to do is take a look at that peel composite and just see if I can extend it to pull in the lighting data that it will use to produce the results, right? So if you take a look at what we've got here, we have the peel sampler 1, 2, 3. Now, one of the things that I think probably was a little bit of a mistake, if we're being honest with ourselves, is that probably what I should have done is use the texture array for these samplers, because if I'd used a texture array, then what I could have done is picked out, either had the peels go on the texture array, each array would be each array element would be a separate peel, or I could have had the array be the information about the different pieces, right? Like the array slice 0 could have been the color, array slice 1 would have been the emittance, array slice 2 would have been the normal, something like this. And so that is, you know, something that I think maybe we could have done a little bit better there. I'm not going to do that now, and the reason is because introducing a new thing like texture arrays leads to debugging. I don't really want to be doing debugging right now, I'm just trying to experiment. So what I'm going to do is I'm going to expand these out first just to have more samplers, because I think that's a quicker way to do the experiment. Later on, we can try to turn that crank and optimize it down a bit, figure out where we could introduce something like texture arrays to reduce the number of samplers, to make things less complex for the graphics card, for graphics cards that don't deal well with things like that. Intel integrated graphics, for example, I think has a little more heavyweight stuff associated with samplers. It's not like in NVIDIA cards where it's kind of just a pointer. And you know, on NVIDIA cards, it's not so clear to me that there's that much of a win to doing stuff like switching from multiple samplers to texture arrays. There probably is a little bit, but it's a lot less drastic, whereas I think there are certain cards where that win can be substantial. Don't take my word for it. I'm not a graphics guy at all, so that may be old news, but that's just my kind of tingle, my little like inclination, my gut tingle, which sounds kind of gross, but there you go. Anyway. So what I'd like to do here is I'd just like to look at what we want to pull in. So what we're going to be getting by default in these peel samplers is we're going to be getting the surface reflectance, which we definitely want because that's the thing we're going to be compositing. But what I'd also like to pull in at that point is probably the normal, because the normal is the thing that we're going to use for the lighting, and so we probably want to pull in the Opengl NPL value there, right? This one right here. So what I'd like to do is take these and just augment them to pull in the NPL for each of these as well, right? So we basically have an NPL sampler for each of the things we previously only had the peel sampler for. So something like this. So we've got peel NPL, peel NPL, peel NPL, peel NPL, right? So we're pulling each of those in. And then the other thing we want to pull in is that lighting information, right? So we also have that to think about. So anyway, we've got each of these peel samplers, and now we've got to compute the lighting information for those. What we want to do here is take a look and see, okay, so we've got each of these texture samples for the peel is now going to become something that lights each of these, basically. All of this stuff here is fine, but when we do the actual, after we've pulled the lighting in, we've adjusted the RGB of it, we're going to want to do the operation to produce the lighting somehow here, right? So, after we've done all of this stuff, right before we start using these peel RGBs, what I'd like to do is augment them all. So we basically want to do like a lighting operation on our peel where we pass, actually I guess that's the NPL sampler. I could, I guess, just take the samples here as well. Like so. So that samples from everything, and now we have our peel and our NPL from each of those. When we take these samples, what I want to do after we've adjusted their RGB is basically modify them using the NPL value and the lighting value, right? So we're going to pass the NPL value, we're going to pass the peel value, and we're going to pass the light. So we're going to have something that looks like this, which adjusts each of the peel's lighting, like so. Now we don't have to do it this way. We could instead try to composite and then do the lighting, but I'm just going to do lighting on each of them first instead, because we might as well spend more GPU time than less at first, because we can always go in and try to optimize things later, but we don't want to do that at the outset because we won't know if our optimizations are causing our lighting to have artifacts that it wouldn't otherwise have. So we'd rather try to do it as well as possible and just slow first, and then we can optimize it by removing things and see whether they materially affect the quality of the lighting. That's usually a better way to go when you're trying to develop a new technique. So we need a couple things to happen here. First thing we need to happen here is we obviously have the light peel that's going to happen here. I guess the RGB does the alpha value. The alpha values are not used at all in this, so I suppose we could just use the RGBs only here. Like so. Because again, the lighting is only operating on the color. It's not going to change the alpha of anything, at least not at the moment. So when we do our light peel, we're going to do that operation. Maybe I should have passed the whole thing. I don't know. It's hard to say. But we're going to take in a V3 and return a V3. And the NPL value itself is that packed V4. And then we're going to have a lighting sample of some kind, which is some information that we're going to need. So I'm assuming the lighting sample is going to need a couple different things. I probably shouldn't call it light sample. We're probably going to have a little bit something more like light P, light direction, right? So there's the light position and the light normal are the two things we're probably going to have. Come to think of it, the light position is kind of already factored out, so it's probably only just going to be the light color and the light normal. Right? I'm guessing that's about it. So those are the two things we're probably going to be taking in here. So we'll go ahead and just pass those along. Oops. Like so. And so what we're going to have for a light normal and a light color are coming in here. And then what we need to do is we need to do a mapping. So we've basically got, got to unpack the NPL data, obviously for start. And in order to do that, we have to do our unpack. The unpack, of course, is pretty straightforward. It's this right here. What we might want to do is standardize on this unpack, because since multiple people are unpacking at this point, it may be better to unpack it in a sane, single way, because that way if we decide to change it in the future, we don't have to worry about it at all. We can just know that it's being done correctly. So what we could do here is basically say, v2n equals something and have that unpack happen. Of course, I guess now that I think about it, we've got sort of two ways, but I guess it's something like this. Unpack normal2, something like this. I don't know what we really want to call this, but unpack, I think unpack normal2 is probably all I'm going to really get, if we're completely honest. So we'll do world n xy, and unpack normal2 will just be this thing. And what we can do is we can put that in our sort of global shader header code, which is this stuff right here, and everyone can use it. So we can have a v2, which is like unpack normal2, and we can take the incoming normal like so. And what I can do here is just say, well, yeah, the result x, so we've got a result here, and result y are going to be equal to these inputs scaled like so, and then we'll return that. So now we can call that unpack normal, and what we can do is, furthermore, we could have an unpack normal 3 if we want to actually generate the entire normal. We could say, well, if we want to do an unpack normal 3, we pass the v2, we can get back the n2 from the unpack here by passing it this way, and then what we can do is generate that final value, right? So we can say result equals n2, and then we just have the equation again for the renormalized part. So we can just say n2x times n2x minus n2y times n2y. And that way we can get back a full normal if we want to as well by calling unpack normal 3. So we have a way of getting either of those back. When we get back this normal, like I said, this is just saying this is the same equation we had before. Let's see if I can find it for you. So here, right? Do you remember when we kind of solved this one, right? Oh, I forgot my square root. Glad I just looked at that. It's the same one here, only this one is reconstructing the normal from two regular components, if that makes sense. So I guess actually we could actually keep this. This function could actually sort of be made in. It's doing almost exactly the same thing, right? So we could, in theory, have this one be reused as well, because that unpack normal 3 is almost the same code. I don't know that I really care about doing that right now. This is not particularly complicated code. But point being, I just want to, at least for the most part, have everything in here be systematized, so I know that it's happening in one place and happening the same way everywhere, and there aren't multiple people unpacking normals in lots of different ways, right? So now when we actually go to pack this, put this into the floating point buffer, we got to actually have the n2, which is the thing that actually holds it now. So if I want to do the unpack here, now I can actually do that rather directly. And since we want to probably unpack that once, what I'll probably do there is just say we'll get that when we actually do the initial sample. Oh, I guess, but the NPL is actually the thing that we need to unpack. Never mind. So we have to do that every time in the light peel. So here is our reflect normal that comes out of the NPL's XY. So in this case, what we want to do is say unpack normal 3, because I want the full real normal. So after we unpack the normal, we also have to take out our two lighting values. So we have our LP0, which is comes from the Z, and our LP1, which comes from the W. Neither of those is really getting used, but we could then use those for specular at some point in the future, right? And so once we've got that, we're ready to compute an actual lighting equation here. And what we can do to produce that lighting equation is just use the lighting we were using before, the kind of poopy lighting we were using before. So let's go ahead and grab that. I saved it. It's right here. So let's go ahead and drop that in. Oops. And we essentially want to do that right here after we've gotten the information out, right, like that. So in this case, we don't anymore have any of this sort of like to camera, from camera kind of stuff that's happening. And the light strength and light distance, that's all the stuff that's now handled by the lighting system. So really what we have now is just the sort of the dot product to figure out how much the light and the surface are aligned with each other. And then of course we do have the reflection vector kind of stuff. We still do have that computation to do for the specular lighting, if that makes sense. But what we can do now as well is, since we have a diffuse coefficient and a specular coefficient that we were using for our lighting, what we can do now is take our LP0 and our LP1, and we can actually use those now as the diffuse light and specular light, for example. So like I said, the reason I wanted to get some parameters in there and actually just have a 4-wide texture that encodes the normal plus that is because I knew we'd use it for something, right? And so what I figured we'd do is just use it for lighting parameters. Right now, since we have a simple Phong thing here, we can just have diffuse and specular as the two coefficients, and off we go. So if we were to say that diffuse coefficient was the Z and the specular coefficient was the W, then we can just get rid of these and actually do this equation as is. So we'd have the diffuse coefficient times the cosine of the angle times the light strength, and the specular coefficient times the reflection angle and the light strength. So that's all, you know, exactly what we would want. We sum those two together, and that's the light that we transmit. Now, technically, the diffuse and specular should not be separate components. So my guess is what we'll do in the future is make these two parameters be something else. Probably one of them should really be because in general you can't just reflect out an arbitrary amount of light. The amount of light, total amount of light you reflect out, should be proportional to the light you take in, and it should be somewhat less than the light you take in, right? No surface reflects 100% of the light it takes in. So in general, you know, you can't just arbitrarily set a diffuse and specular coefficient. It doesn't make any sense. So in the future, we may want to play around with that a little bit, but let's not get bogged down in that just yet. Once we actually have better lighting transport going, then we can worry about fine-tuning the lighting equation of the final gather. So anyway, what we need to do now is tune these equations that we had before to use the information that we probably think we'll actually have from the light transport, which is not as straightforward as what we had in the past. So in this case, we're going to have a thing that's basically like, what direction is the light coming from at this point? Like, what's the overriding direction? And so when we were doing that before, we had the 2 light thing here. And so what we're going to have is 2 light is going to be this light N now, right? Like so. And our reflection normal is going to be this. Now, why we were doing this multiple times, I'm not entirely sure. It seems like we want to replicate that out, so we probably want to do something here where we take, yeah, like this looks just kind of busted. What we really want to do is the like dot term, so the reflection dot term, right? Let me do an inner product here. Let's do this. So the inbound lighting direction and our reflection direction, we want to negate that because the way this was phrased originally was the direction that goes out to the light source. And in this case, we're probably going to end up with a thing that says where the light source is pointing towards us, right? So we're probably going to have to use a negative in terms of the light normal at this point. And then we're going to have the reflection direction. That's actually just correct. We're going to dot those two together to see how coincident those two are, and that's the information that we actually need for our ref inner. At that point, we're going to clamp this because obviously we don't want, so I can just put that here. We don't want this to go negative. You can't have negative light. Well, you probably could in the real world. Some scientist somewhere probably has figured out how to create negative light. But in most things we observe, there is no negative light. So we want to clamp that to 0 so that we don't contribute a negative value. So here's our cosine angle term, and it'll be used down here in the diffuse lighting. We could, if we want to, sort of make this a little bit clearer by there having the diffuse light computation, and here's the specular light computation. So here we go. So now we've got our total light, that's the sum there. So now we have to figure out here in our specular light, we've got to figure out how to get the 2 camera, right? So that's how do we get the world P out of this, basically. And that's probably something that's going to have to be passed in here, right? So this is going to be something that's going to have to be passed to the actual light peel itself, because there's really no way to get that information without being outside and knowing more, having more inputs than this. So we're going to have to pass that in. And so here's our reflection vector, the negative 2 camera plus 2 times the dot. I don't know why I was typing dot instead of our inner. They're the same thing, but I usually like to use my own terminology. So then we've got our world normal, which in this case is just the reflection normal. We've got the 2 camera, which is getting passed in. And again, we've got that reflection normal here. We've then got our cosine reflection angle. This is the reflection vector, which is basically the reflection of the camera out. So then we take a look at the dot product of that one. Again, I don't know why we phrased it that way. So this is the ref vec dot here, and maybe what I'll call this is spec inner, and this diffuse inner. So that's really all we're talking about here. Again, we've got sort of a negative light n. Maybe I should just go ahead and say 2 light equals negative light n. And then I can leave these phrased without the negative, like so. Probably not worth it. Like, probably what I should do is just negate the inner product, because that's what's coming in and it saves some computations. But what are you going to do? I'm going for cleanliness at this point and ease of readability. Later on, we can talk about if we need to do anything that the compiler can't itself do in the shader to make things faster. All right. So here's us computing the reflection vector. You can see it's fairly straightforward. We've got the specular inner term now, and we can now create our vector of that. And then at the end, we don't need to clamp this because we already did that right here. We've got our power, right? Our specular power. Now, this is something that we're probably going to want to... I think there's a POW, basically, for doing specular. You can see it right here. So you can basically say you want to raise this thing to this power. And so what I think we probably want to do here is actually do something like cos ref angle equals POW, where we can take in the cos ref angle and put in a power. So in this case, it was 1, 2, 3, 4, 5, 6, 7, 8, 9, something like that, right? So 8 or 9 power, we can just put that in there. And the reason that we want to do that is this is probably going to be the way we're going to do our lighting parameters in the future, right? So probably, and in fact, let's just do it that way right now. So let's say we have a specular power. That's going to be MPLW. And let's say that our specular coefficient is just 1 minus the diffuse coefficient. Now, that's probably not correct. We'll have to think about that. So we'll think about that a little bit more, but let's just say that this is the diffuse amount, so the specular amount is just the inverse of that, so you know it's basically a complementary amount. And so at that point, you know, we're just sort of producing the diffuse color and the specular color as a linear blend, basically, right? We could even phrase it that way if we wanted to as a lerp. But here's the diffuse light and the specular light coefficients together, and now the cos ref angle, instead, we can put in the specular power as an actual function, which means we can have surfaces that get tighter or wider reflections coming on them, right? So we'll sort of deal with that a little bit later on. So once we have the total light, we need to compute an actual result color. So the peel color that comes in, what we're going to do is modulate the total lighting amount by that. However, we have to remember that the total lighting value at this point is actually not quite a sane value, because we're saying that lighting is going to kind of have a maximum. And I believe we said max light power here. I want to sort of define this as a global variable that we can tune however we want. And the way this is going to work is we're going to say what the max light power is. And I guess we'll call this max light intensity maybe. And so what I want to do here is the max light intensity is going to be something that we're going to divide out. Now what this basically is, and because we haven't gotten to this point yet, and maybe in the future we'll play around with it a little bit, I don't know. But essentially what we're doing here is like the poor person's tone mapping, right? So typically what happens in systems when you're dealing with any kind of realistic lighting at all, which we're not really even doing, but we're just taking it far enough that we're sort of stepping into this realm where it becomes relevant. What we need to do is the total lighting value at this point needs to be adjusted to the fact that it was a much higher range than it was than the 0 to 1 range we actually render. So at some point when we're done, we have to take these lighting values that may be like 8 or 9, 9.6 might be a light value, right? We have to shrink those down to the 0 to 1 range. So what we want to do is take that total lighting amount and map it in some way that makes some kind of sense. Now there's a lot of ways that we could do that, but we have to be careful, because if all we did is a linear mapping, what you can see if we do a linear mapping, let me try to demonstrate the problem here. Nope, that's the web browser. Okay, there we go. So what we get, let's see here. Go back. There we go. Nope. Milton. Bring me your, there we go. All right. So day 398, light value mapping. So what we're going to have is in our system, we're just going to have something which it has to map sort of these linear light values to output values, right? So what we're going to have is something that takes, you know, our output value. We know that it is constrained between 0 and 1. Because even if you have a high dynamic range monitor, you're still talking about some range it can display. Where 0 is the darkest thing it can put on the screen, and 1 is the brightest thing it can put on the screen. But nothing, you can pass it an arbitrarily high value to this monitor, it's never going to get any brighter than the brightest value, right? So when the DAC, when you finally get to the point, I can't believe it's not a DAC anymore, right? It's all digital. When you get to the point where you're actually driving the OLED, right? There's some maximum on and maximum off signals that you can send to adjust what the actual element is putting out. So when we talk to that monitor, we're just talking about a range of 0 to 1, where 0 is the darkest and 1 is the brightest. That's all we can do. So we don't have infinite levels of brightness like the universe sort of does. The sun versus a lamp in my room, the difference between these two things is so incredibly vast, and really there's not a lot of limits on how much photons can be flowing per unit time in a given area. Now, in theoretical physics, I'm sure they figured out that there is some limit. Like, you can't have an infinite number of photons in an infinitely small space, I'm guessing. But what do I know? I'm a programmer. I don't study physics. I have no idea. Maybe you can. But what we definitely know is our monitors definitely can't. So our monitors are only producing a limited amount of photons. And this is the maximum amount that they can produce, and this is when they produce the minimum amount. So what we need to do is take our conceptually infinite values, because we can set a floating point value to things that are absurdly high, right? And so we need to figure out a range of our floating point values. And so that's, in our case, 0 to whatever max light power is. It's just an arbitrary value, right? And then what we need to do is we need to take whatever this max light power is and we need to map it to the 0 to 1 range in some way that makes sense. And typically what we want to do is we don't want this to be a straight linear mapping, because our light power is something that makes sense only in the units of our light simulation in the game. In our case, it's completely arbitrary because we're doing purely artistic lighting. But even in a game where you're doing physically accurate lighting, it's going to be in something like lumens or photons or something. You're going to have a number that has nothing to do with the monitor's brightness level. It's not going to be 0 to 1. It's going to be some other value that doesn't relate at all to monitor gamma or any of these other sorts of things. So what you need to do is then take that and you need to map it into the visible range of the monitor using something that gets you an image that you want. And so typically what you want to do is do something that looks maybe, here is like the linear mapping. This mapping is not going to be very good. The reason it's not going to be very good is because if you imagine that lighting fall off is nonlinear, and you're going to get these sort of very, very high values in the locus of a bright light, and then anything that reflects that light is going to be drastically lower, you end up with a scene where you can't see anything other than the lights, right? Because reflected light is down here thanks to the inverse square law, and emitted light values are up here, right? And you don't want to have a scene where the lights are infinitely brighter than everything else around them. That's not artistically satisfying and is not going to produce a very interesting game. That may be an accurate representation of how much light is somewhere if you're doing physical light simulation. It might even be right. It's just not satisfying. It's why people pick different types of film. It's why CCD sensors on cameras are adjusted certain ways. It's why we have tone mapping and saturation and all these other sorts of adjustments we do. So you want here some kind of what's called a response curve. And what you're doing here is you're sort of simulating filmic response or something else. If you're pointing a video camera at something, or your eye's response curve, the way your brain maps the number of photons that hit something in your cells, right? Those sorts of things. You want to come up with a mapping here that makes some sense. And typically that mapping probably looks something like this, right? Which is to say that somewhere inside where we expect the reflected light to largely be, we're going to have that take up most of the 0 to 1 range, and then just the top end of it is going to account for the rest. Just 0.9 to 1 is going to account for all the rest of that that area, from 2 to max power or something like this, right? And so in order to do something like that, we want a curve that's very bowed out, right? So we want a curve that's more of a square root curve or something like this, or a multiple square root curve, to do that mapping to kind of flatten it out. Now, if you're really doing this stuff seriously, right, and we're just going to hack one in now, maybe we'll do a better one later, I don't know. But if you're doing this stuff more seriously, then typically what you end up doing here is you end up studying other classic response curves to construct something that's a good approximation to one of those. So for example, one thing you might do is study the filmic response curves of classic Kodak film stock used to film great movies, right? Because there is a whole industry that spent all of its time trying to come up with chemical processes that would produce good-looking images for cinema. That's very similar to what we want to do, so taking a look at their response curves is a great way to figure out a curve that will map lighting simulation that might have something to do with the real world into something artistically pleasant. So what you'll do, if you're looking at filmic response curves, is you'll take a look at what the actual measured physical response curves were of real Kodak film stock or other kinds of great film stock, and you'll piecewise fit polynomials to them to approximate them. Just classic functional approximation theory, nothing fancy, just basic fitting of a polynomial to some data points, kind of a thing. And then you'll use that to translate your incoming values. We're not going to do that, obviously, because again, like I said, that's getting a little bit out of the scope of what we might want to do here on Handmade Hero, but just so you know, that's something you can do. That's what high-end rendering does. And furthermore, it often gives the artist the ability to tweak those curves to their liking. What we're going to do instead of just something approximate, I'm just going to use probably a simple square root curve. That's not great. We may want to do something a little bit better later on. but we're going to do something like that. So I'm going to first divide by the max light power to put us in the 0 to 1 range, and then I'm going to bump that curve up by like gammaing it up a bit, like square rooting it up a little bit or something like this. And we can play with that curve all we want to produce something more reasonable later if it so suits us. So here what I'm going to do is I'm going to take that light end, and whenever we get the light end, what I'm going to do is I'm going to take light end divided by max light power, or light intensity rather, which that scales us to the 0 to 1 range, or at least it presumably does. We will then do a clamp 0, 1 on that to produce a value that's reasonable. This should have been a clamp 0, 1 as well. I don't know why it isn't. So we're doing clamp 0, 1 on that value, so that gets the value between 0 and 1. And then what we want to do, again, like I said, is just adjust it a little bit here. I'll put that as a separate thing. Let's say we do a squirt of the light end here. And like I said, we can do that as many times as we want if we want to bump that curve up or down. If we wanted to flatten the curve, to do it the other way around, which I don't think we do, but if we did, we could square it, such and so forth. All right. So assuming that we're doing that, right, and we figure out something good here. Again, this might have to be really flattened out. And what you can do, you can imagine this, like let's say we go to Wolfram Alpha, or we could even just, I think Google will do this if we just say graph square root of x. I think it'll just draw it for us. So you can see that curve there. If we double square root it, that's probably more what we're looking for. Right, like something that has a pretty steep curve like that, But again, probably what we really want is more. Let's make sure we're looking at the right range. So here's the 0 to 1 part of this, right? I don't know how to. There we go. So yeah, is that really what we want? Probably not. Like we'd probably want this part here to be a little more linear and not so attenuated. So I don't know, but we do like this kind of long curve here. So yeah, like can we do better than this? Absolutely. I'm just not 100% sure what the quick and easy way would be to do so. But again, we're just going to leave that for the moment, and we will come back to that later when we need to, right? When we need to sort of make that a little bit more reasonable, right? Okay, oops, that's light N. I want light C. I don't want to do that to the normal. I would do that to the color. So we need to sample light C and light N here. Those are values, obviously, we need to grab. And they're both B3s. And so those will be texture samples from the lighting information that we have. When we sample the light N, we will be getting that pretty much from these will both be coming from different textures. Let's see here. And really, because we have front and back emission at the moment, I suppose we technically could sample 2 light values here if we wanted to. I'm not sure that we need to just yet, but yeah, maybe we should, right? We'll have to see what the... Let's think about this. So when we do light peel here, we essentially have to compute sort of this equation twice, one for each light, if that makes sense. So what we could do is just add those two together fairly straightforwardly, actually. So if we wanted to, here, we could do something where we did this, where we actually took the 2 lights, the front and the back, the two lights that we're getting, and combined them together, right? I'm going to hold off on that. because we need to keep thinking this through, and I feel like we're going to progress the lighting a couple more times over the next few weeks. So I'm going to hold off on that just yet, because I think we've got a ways to go, and I don't want to overdo it. So I'm just going to stick with one first, and then we'll kind of start pushing that stuff a little bit further later as we go, right? So here's our light peel. We know we need to pass to camera here, like so. And actually, this reminds me of something I wanted to try. So let me go ahead and compile this. I wanted to know something about these here docs. One of the problems that we have, as you've noticed, is we don't get any indentation on these because 4Coder thinks they're strings. Because, hey, guess what? They are strings. I was wondering if there might be some way to fix that. And I just kind of had this harebrained idea, and I don't know if it actually works because I don't know much about these aren't actually C++ here docs. They're actually the other kind of string. There's two things in C++. There's the here doc ones, which are actual here docs, and then there's the C++ extended string thing. I don't know why they have both exactly, but they do. There maybe was a reason for it. It may just be one of those C++ things that they messed it up the first time, and then they made another one that's probably also messed up, and so now you got two messed up versions, neither of which work. But either way, that's what we've got right now, and I was wondering, could you do a pound define that contained the here doc notation in it? Or sorry, not the here doc, whatever you want to call it, right? Like, could you do something that included that in the pound define, like so, like open string or like shader string, and then it was like, or I guess even we don't even really need the name. I guess we do it like this: begin shader string, end shader string, something like that. Oops. And I don't know, it looks like 4Coder has a lot of trouble with that. I don't know if this is the correct interpretation of this. Maybe the problem is that you can't put this in a pound define. But I was saying, like, if you could put it in a pound define, then what you could do is you could use the pound define instead of this so that this would still have indentation, right? I was just curious if that would be possible. I don't know if it is or not, though. Let's just find out if I can even compile it. Nope. What? I'm not sure what exactly that's. Vertex code undeclared identifier. I'm assuming that basically what happened here is that this just gets skipped out on. So I'm assuming what happens here is that you can't put it into a macro. So, oh well, right? I don't think there's anything you can do about it if you can't put it into a macro. I just had this faint feeling. I was like, I wonder if there's some way we could do something there. But it doesn't look like we can. The other thing I was thinking is, could you put a pound include in it? But then I was like, no, because the pound include would be part of the string. So you can't even import stuff into it. So unfortunately, the only way we'll ever get it is if we decide to load these out of a file separately, essentially. So yeah, that's where we're at, which we could do. It's not the end of the world. Anyway, so off we go. We've got the light peel computation in here. We need to sample these from somewhere. So what we need is our light sampler, like our light color, and our C sampler, and our like N sampler. So the color sampler and the normal sampler are both going to just sample from the lighting computation that we had. And the light normal is actually going to be the NPL texture for the lighting. Which again, this one right here with the depth. So this is really the light NP. And I guess this is the emit sampler, like so. So to get the light C out of that, we have to do an unpack of these values, right? And in order to do that, again, we need to do a like sort of a z extend. And again, we can just make this. This is probably the part where it's good to pull this out. So light n equals like extend or extend normal z, something like that, where I can basically pass in the xy and get back the version with the z being the 1 minus square root. So if I do something like that, then that also gives me the way to do the thing I wanted to do before, which is make all of these be things that operate that way. So here's the v2n in this case. And basically what we're talking about here is you don't have to do the unpack, you just do this, because the other two values are correct. And so at that point, this function becomes extend normal z of unpack normal 3, or 2 rather, of n. Right? So that way we can do all the different versions of it. So here where we do reconstruct normal for the v3, really all we're doing when we pass the np there is this is just the normal extend. So this is just going to be v3 result equals extend normal z np xy. And then that's it. So now that computation has been pulled out, which is good. Now, thankfully, last time we did a thing where we took out the sort of the sampling stuff and made it automatic, so that we don't really have to do too much work to extend the fact that we've got a bazillion samplers in this particular situation here. So what I want to do inside this is I want to get my light emit sampler and my light NP sampler. And I also need to do these peel and NPL samplers. So I just want to get all of those assigned here. So it's like this sort of a thing. And then we've got a light emit sampler and the light NP sampler. And so all of those samplers will now just get linked up, in theory, automatically for us, which is nice. Because again, it was a pain in the butt to have to do those all the time. So it's nice that we kind of made it automatic. And so what we need to do at that point is we need to actually load it all up. Because, yeah, we got them bound now, but that doesn't really help us because we have to actually put them in here somewhere, right? So what we're going to end up with here is we're going to end up with a double bind, if you will. So we've kind of got this situation where we need to do 2 binds for each of these. So we're going to actually bind 2 textures for every peel, like so. We're going to have to bind the basic surface color one, but then we're also going to have to bind the MPL one, right? So once we read those 2 things, now we've got all of those bound. We still have to bind at the end 2 more textures. We've got to bind the 2 textures from the lighting solution. So we're going to have to do something like this. And at some point that becomes a little bit onerous, so maybe we even just want to do something like that. Where every time through here we just say, the heck with it. Bind them all. Right? And so, yeah, I don't think we actually need to unbind these the way that we were doing those before. So I'm going to actually get rid of this. So what we need to do here is we just need to make sure that we're binding the light solution here. So that's going to be from the Opengl light buffers. And for the Opengl light buffers, we're going to take that base level solution that we, quote unquote created, which we really haven't created yet, but which we have sort of a dummy, crappy thing in right now. And we're just going to take the front emit for the emission, and we're going to take the NP for the NP, right? And that's it. All right, now we probably have a ton of stuff to deal with error-wise, so let's get started. That's not helpful, but we can take a look at the actual error here. Skip over that statement. Let's take a look. Yes, I know. Okay. Undeclared identifier light S. That is not good. There should not be an undeclared identifier. Obviously, light S. So that's the light strength there. And the light strength in this case is just the light C. All right, let's recompile that there. Let me see if there's anything else. I don't know. No, 2 camera. So in this case, we have to have 2 camera in here. And that we haven't determined yet. So at the moment, we'll need to compute this based on the camera and the fragment UV coordinate, which we don't actually know yet. So what we'll do here is we'll just, because we need to use the depth value at each individual point to determine that, to determine how far away the thing is, I suppose. Although, well, I guess, no, we don't actually care, because this 2 camera is a normal vector. So actually, we know just from the UV what it actually is. So that, we don't actually need the depth to compute that. So we know that it's, the normalized version of like the frag UV, and we just need to know the FOV in order to compute it. So for right now, I'll pretend that it's just the Z vector pointing upward, but we will be able to generate that in the future, for real. And we won't need to read from the depth buffer to do it, I don't think. Let's see. Cannot convert high 3p vector of float. This is no matching overloaded function found for POW. Okay. Oh, yes, that's right. That POW, I think I accidentally put it after yeah. This is supposed to be on the spec inner. That was just a screw up. So let's see. Cannot convert 4 vector float to high 3. So we've got a 4 to 3 downsample problem there. I don't know where. But we will try to figure it out, probably right here. And so now we have to go ahead and actually see what this does. In order to see what it does, we're going to need a way to look at the actual output of the game. What I probably want to do is have some way of looking at the debug light buffers as a parameter, so like we can switch between viewing the debug buffers and not viewing the debug buffers. You can see not particularly impressive here. This is not a good result, to say the least. That is a pure black screen. But so let's debug that first, but then it would be nice to be able to switch between those, so let's put in something that we can use to switch between them. So here's compiled depth peel lighting. The compiled depth peel lighting pass. I'm sorry, not compute depth peel lighting. That's not actually what I want. I want the peel. Compile peel composite. So the peel composite, we have to make sure that this is actually doing something vaguely correct. And in order to do that, the first thing I want to do is figure out, are all of these samplers actually getting bound properly? Because I have no idea if they are, right? I have no idea. So the first thing I would like to do is turn off any computation whatsoever. So let's just see whether we're even sampling these peel values correctly at all. Okay, so that looks right. So at least we know that the peel compositing is working just fine. So it's just the other parts of our sampling that aren't working. So let's go ahead and get rid of this and go up and work on the light peel function. I'm going to start with the simplest possible thing just to make sure there isn't anything too stupid going on, which is I'm just going to have total light set to 1. So I should see the same result here that I saw before, and I do. So that's all we really need to know now. We know that we've got problems in here, so let's start working on making those correct. So the first thing I'm going to do is I'm going to go ahead and say that we will just light based on the normal, and we won't try to do any other part of the lighting equation, right? So let's take the lighting coefficient out of the equation. So let's just say we have a light C, or actually, you know what, we can double it up. We can even say, let's assume that the light normal is just pointing straight down, and let's assume that the light is full bright. So what we should see here is we should see a fairly consistent image now that doesn't have any real problems to it, right? It should look roughly correct, the same as what we had, and it does, right? Now there is a little bit of weirdness there, something that doesn't make a whole lot of sense to me. The normals for the reflection, for the peel itself, should have been doing some kind of attenuation there, but they didn't, and I'm not sure why. Because again, regardless of whether we're doing specular or diffuse, we should have had, oh well, you know what, if we were, no, but either way, the reflectance normal is going to vary in this case, and we should have seen that variance occurring, but we didn't. So what I'd like to do is let's actually try something else first before we go any further. Let's try taking the result and let's just write out what the normal is at all, right? So let's take, say, the NPL and write out the NPL directly. Right, so here's our NPL, and so this obviously is varying, which is what we expect, and which is good, right? So now let's try taking the dot product and doing something there. So let's suppose we took our 2 light, which is just the negative of the light n, and let's inner product that with the ref normal that we got back from unpack normal 3. And I guess the other thing, well, you know what, let's do this. Let's actually do ref n and see what that looks like. Because maybe that function's busted. Parse error. Must have a typo there. Oh, yes. So this is the ref n. This does not look good. So I think we've got a problem there. Here's the NPL. We called unpack normal 3 on the NPL. The NPL should have been more sane than that. So let's take a look at what we're getting here. Let's take a look at unpack normal 3 and see what the issue is. So unpack normal 3 calls unpack normal 2. Unpack normal 2 takes that n in and does the unpack on it. That's the pack. So this is just a straight up bug on my part. Yeah, this is the pack. This is supposed to be pack normal 2. I don't know what I was thinking. This is the unpack. So I'm just stupid, is basically what this boils down to. So let's try that one more time. So in this right here should be the pack, the unpack rather. It's that code right there. And where are we doing that? NXNY. Or whoops. So I think that's all we want to do there. So we have the NXNY, and there is no N in here, so that shouldn't conflict. So now we actually have the actual unpack normal 2, which is what I actually wanted, right? So this is actually pack normal 2, and this is unpack normal 2. So unpack normal 2 actually does this operation. Pack normal 2 does this operation. So that should now be more what we were expecting. Undeclared infer NPL. Right you are. Here we go. Cannot convert from float to 2 compared to a float. Unpack normal 2. Also correct. That requires an XY. All right. There we go. Now we're looking much more sane. That's more what I wanted to see. All right, so now our normals are looking looking more like what we want. So I can go back to taking the lighting equation there. Let's take a look. There we go. So let's take a look at what happens if we, well, I guess what I can do now is let's see what we're looking at for the actual equation now with the light normal and the light color like locked in. So that still doesn't seem to vary by the normal at all, which is a little weird. So let's keep going. Let's take the result and we'll make the result be equal to the diffuse inner product. And what we should see here is that when things are tilted, we should see excuse me. When things are tilted, we should see them have a difference, right? And that looks roughly correct. At least I think it does. I'm relatively happy with it, at least. So let's take a look at what happens here. We also, I guess, have to look at the specular. And remember, the specular has been raised to a power as well. All right, well, that answers that question. So it's the specular. We probably have the diffuse coefficient set to 0 right now. because LP0 is not set to anything in particular. We could reverse these and have the diffuse, but for now, let's just take a look at why the specular is sort of in the state that it's in. What happens if I don't raise it to the power? Is it just the power part? Yeah, so it's just the power part that's operating in an unusual fashion. I'm not sure why that would be the case. Probably because maybe specular power is 0 in this case. So we probably want specular power as .w is going to range from 0 to 1. So we need the specular power to mean something else. We probably want the specular power to be something like, you know, oh, well, you know, it's anything from 1 up to 16 or something like this, right? Or in this case, 17. Let's try 16. Right? And in this case, too, we sort of have a situation where I don't even know why I would bother with these, because if you wanted the surface to be diffuse, you could just set the specular power to 0 and get that. Oh, no, you couldn't, because it's still directional. Yeah, all right. So that's fine. All right, so now I think we're at least closing in on something semi-sane, barely. So here we go. So now at least we're getting, you know, quote-unquote lighting from a fake light source, not any real light source. So let's go ahead and take the light color out of it and see what we get here by having the regular light color, and we get nothing. So that is less than inspiring, to say the least. And I'm not sure exactly why we're not getting anything there. We're sampling from the emission. I guess here's a question. Have I made sure I actually computed those buffers yet? Because I may not have. Ah, yeah. So obviously we have to compute the light transport. That has to happen. And we weren't doing that. So we can get rid of fake seed lighting now, because that's not actually something that needs to occur. So we can get rid of that. Yeah, I guess we're just that. Like so. And compute light transport just needs to happen higher up the pipeline, right? So before we do anything further, when we're going to do this resolve here, we need to have computed the lighting prior to this operation. You know what I'm saying? So like right here, before anything else happens, the light transport has to be handled at that time. All right. So now you can see we at least have some of, you know, we have something happening, right? But it's not obviously anything that we would want to use yet. I guess one of the other problems we have with this, just looking at it, is the lighting artifacts come through in like in the actual final image, which is a little bit of a bummer as well. So I'd have to think about how we're going to address that. That's obviously going to be something we need to figure out. But anyway, let's go ahead and finish this off by taking the light normal as well, which I don't think is going to really do anything. But we might as well just get to the point, like I said, where everything is sort of flowing in properly, and then we can talk about how to start improving this to make it look like something we actually want. So let's see here on PL Composite. When we come through here, I'm not going to nerf the light normal anymore. So we'll actually have the light normal be meaningful, or at least semi-meaningful. That does not look reassuring. What is wrong with our light normal? Oh, well, part of the problem with our light normal, yeah, at this point is the lighting calculation just doesn't do anything interesting with the direction the light is actually pointing. So now that I think about that, that's really not super useful either, right? Because really the light is always going to be coming in at any given pixel, the normal is going to be the same because we don't currently weight the normals when we average them together, so that's not going to be helpful at all, right? So that is a non-useful thing at the moment. Yeah, so we have to kind of nerf this if we want anything to happen there, if that makes sense. Oops. All right. So, but we did do what we wanted to do, which is to say that we have a way of now mapping the lighting results out into the actual game render. We just don't have a way of doing it in anything that looks nice, right? So our next job is to sort of start to try and improve what we're actually computing for lighting in this case. So what we want to do now is have a way we can switch to our lighting buffers so that we can see what they're actually computing at any given time. And in order to do that, let's go ahead and make it so that the code at the end here, which sort of copies things to the frame buffer, let's go ahead and make that be predicated on the debug light buffer text index. So the debug light buffer text index thing, we just want there to be in the Win32 where we sort of have this light buffer text index up and down bit. I don't really know at the moment how we're restricting that. Oh, here we are. This is the clamp right here. So what I'd like to do there is I'd like to say, okay, if the Opengl debug light buffer index is greater than 0, then we'll go through this path. And when we go through this path, we'll clamp it to I guess it's really, honestly, it's this one. It's the debug light buffer text index is really the one we want. If that's greater than 0, then what we will do is we'll come through here, we'll clamp these, and we'll say that this goes from 0 to 4 instead of from 0 to 3. And then when we actually use the light buffer text index here, we will just subtract 1 from it, so that 0 now means we're not viewing any of them. So I think then at that point what we can do, oops. So the problem here is the clamp. If the clamp, we need to do the clamp first, because if it's out of range value, then we need to make sure that we don't get into that routine. But why is it saying it's an invalid enum? How do we shouldn't ever be able to pass anything that we weren't passing before, because debug light buffer text index in this case, it has to be greater than 0 to get in here to begin with. So the fact that I'm subtracting 1 from it should not produce any values that it wasn't previously producing, I should think. And then at the end, the GL rebuffer call of GL color attachment 0 should never, like that should always be legal. So where are we when this happens? What's happening here? It's this one. I take it. Let's double check. So we come in here, yeah. So it's actually just this call, the GL read buffer call. So I guess we just can't call that if we haven't bound a frame buffer yet. I don't know. I thought we already were doing that, but I guess not. So here we can switch between our lightings. I'm going to switch which one is shifted and which one's not. So now shift plus and minus actually just goes up the levels of detail, but here you can see the different buffers now, right? So there's like the lighting buffer, and there's the final buffer that we produce. And you can see in here, like, I don't know what is happening with that showing through there, that sort of artifacting. I can't quite tell exactly what is causing that, which is a little concerning. My guess is it's an overflow issue, but I guess now that I think about it, I can't really think of how it is an overflow issue, because in theory the peel composite is always clamping everything. So I'm not sure how it could actually do that, unless the diffuse plus specular light equation actually blows out to higher than it should. We could try just to see, but I'm not optimistic that that has anything to do with it. Yeah, it doesn't. So in theory, let's just verify that this is correct, because I want to make sure. So in theory, if I was to not call any of the lighting code, I should get a correctly composited pretty image, right? With none of those artifacts, and I do. So I just want to make sure it's strictly in the lighting, and it looks like it is. So that's all I really need to know. And then we're okay moving forwards, because the lighting is the thing that we're working on anyway, right? However, I do see some sparklies. Like, I see some sparklies in here that I don't remember seeing much of in the past. That might just be because of the downsampling. But anyway, so as long as I know that all this stuff is based on the lighting, then that's okay, because that's the thing that we're working on anyway, so I don't mind too much about that. So what we need to do now is take a look at this equation and see, right, like what we want to sample in this case. So a couple things come to mind here, right? When we take a look at what we're sampling, for something like the specular coefficient, the specular coefficient really wants to sample directly from the actual reflection to a certain extent, right? And the degree to which it's going to sample, the width sort of that sampling is going to be based on the power. So let's just talk about that a little bit here in terms of what we want to have going forwards. Also, I don't remember what time will we be ending in like 15 minutes? Is that correct? I want to say we'll be ending in 15 minutes. Doesn't this thing have a way to tell me that? You guys have fancy stuff that you've made. 31 minutes until Q&A. So I actually have half an hour. Okay, good. All right. So what I was trying to say there was, so in terms of diffuse mapping, we want to sample the whole hemisphere of incoming light, right? And the only thing we really need to do to that hemisphere is we need to attenuate it based on the facing angle. So, like, you know, the amount of light we get from something here in terms of its ability to diffuse outwards is going to be modulated by the cosine of the angle, which diminishes as close to 0 at this point, right? But we are trying to take in all of this nonetheless. So even though things out on the very fringe contribute less light than they would otherwise, we definitely still want to sample pretty much everything. Whereas with specular, we're talking about something where we're sampling only within a cone that's kind of going out into that lighting hemisphere. So in the best of all possible worlds, what we would be able to do is we'd be able to sample different resolutions of stuff. So what we'd want to sample in this case is we'd want to be able to take the direction that we want to look in, and we'd want to be able to take a sample that was all of the incoming light across the whole hemisphere and somehow modulate it, right, by the cosine incidence term, which, you know, maybe that's pie in the sky, forget it, whatever. But that's what we would want in an ideal world. So when we go to do something like this, we want to take a very averaged sample. And the tricky part about this, the reason that it's so annoying to try and figure out how to do it, is at every location that we might want to sample it, we then are therefore responsible for coming up with some measure of how the light is flowing through in all directions, right? That's the tricky part of the problem. So we end up in a situation where we are trying to find the lighting direction at any given point. We're trying to find like which directions the light is coming from and how much light is coming from each of those directions. And we don't really have, like I said, we haven't really quite cracked the problem of how we're going to do that. I kind of played around with some ways we might do it, but we don't really have it quite yet. And furthermore, for the specular, we want to do a similar query, but we want to restrict the range. So, you know, if you imagined we had a cube map at every pixel, right? Like magically, we just had a cube map at every pixel somehow. Then what we would be doing is for this case, for the specular case, we would take the nth MIP level, right? Whatever the nth MIP level of that cube map was, average down, 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 down. We would take the nth MIP level of that cube map and we'd sample it, and the n would be based on the specular power. So the wider the specular power, the further n we would take. And for the diffuse, we would take the final MIP map, the one where each of these is basically just a solid color, right? And that's effectively what we would do. And I don't really quite yet know how we're going to get to that level of lighting simulation. What I do know is that we need to start treating in our light simulation, we need to start treating the direction the light is coming from as something that we're properly aware of. Because right now, we're really not quite doing that. We're just kind of averaging things together in a haphazard way, and we're not even weighting the average by the contribution, the emittance at all. So the first thing that I would probably say is let's just take a brief look at how that would work. I'm just going to start playing with this. Again, I have no plan here. I'm literally just experimenting to see where we can go with this. I don't have any plan whatsoever. So let's look at the multi-grid up. So here you can see how we're doing multi-light up. The way that multi-light up works is it just takes a texture sample from each of the locations and bilinears them together, right? So this texture call right here will take the 4 neighboring texels from whichever sample it is, and it will it'll just go ahead and give you back that value, right? Now that isn't really what we want to do in this case. Right, what we want to do is something smarter here, where we're actually talking a little bit more about how the emittance is flowing through. And so we have a couple different ways we could do this, like I was saying before. And I'm not sure which of them is really the right way to go. I kind of started down the route of doing the sort of imaginary like discs that reflect and shadow. But I just don't know if that's a plausible way to continue through it, especially because we sort of don't have a very 3D scene, and we have that ceiling problem where we would need at least a sandwich layer of things to reflect down, because otherwise we just have a ground and no light will ever bounce around because it can't bounce off of anything, right? So we kind of have a nasty problem in that sense, and I don't know, so I feel like we need something hackier. We need something that treats the light more like a fluid than real light in a way, so that it kind of just flows out from things, and we just want to kind of stop it from flowing in areas where there's tall stuff and let it flow in areas where there's not, or something like this. And I'm just not sure exactly what that wants to look like. But what I would say here is that we obviously want, I think, to start having the downsample be more controlled than this. And the problem with doing that is right now we are not really we're not power of 2 at all, and that's not great. So I don't know if maybe we should try to force to a power of 2. I'm not sure how effectively we could do that right now. Let's take a look at what it would take to do that, and then see if we can do a straight power of 2 downsample so we can reliably just take a 4 and move down by 4s, although we may need to do something a little fancier. But I'm just curious. So if the texture width and the texture height for our light buffers were not based on the render width or render height in this case, what would it look like there? So let's suppose that what we did instead was say, okay, we're going to take the next power of 2 down. So we're going to say that we want to basically bit scan the thing and take whatever the highest bit is that's set. That's with all zeros is going to be that's going to be the accuracy with which we're computing the lighting. So taking a look at that, let's say we did thought we had a bit scan. Maybe not. So we do. We have find least significant bit set. I don't really remember why we were using it. What did we use this for? Okay. So we just wanted to find when we were looking at the thing for reading in a BMP. That's what we were doing. All right. Well, there you go. So what we really want to do is do the bits the opposite of this, right? So we want to do something like this. I'm assuming there's a bit scan back. I knew I'd guess it eventually. So there we go. I believe this will work correctly. Test equals 31. Well, you know what? Let's do it this way. All right, so assuming that we can call this now, we should be able to do what I wanted to do, which is find the power 2 that's, the most related here. And instead of setting the light buffer count at the outset, we could just set the light buffer count based on that. So what I could say is, and in fact, let's do that first. Let's not do this yet. Let's go ahead and take light buffer count and make that equal to 0. And then each time through here, we'll just instead of doing this, we'll just assume that it's true. We'll loop through the light indices. In fact, we don't really even need to do that. We can just say, because light index in this case, I believe, is only used there. What we could do is just do a for loop that keeps on going. And each time we do one of these, we do like Opengl light buffer count plus plus. So we keep going, and then down here we do, in fact, I could just make this a while loop that basically says like while text width is greater than 1 and text height is greater than 1. So once we collapse down to, and we probably, like I said, in the end want this to be like no less than a 2 by 2 or something, right? Because we probably don't want the lighting to collapse down quite that far. I don't know. But for now, all right, we'll just say we'll go all the way to the 1 by 1. So let's see if that works at the moment. Again, I think this should just produce the same results we had before. So that's all good. And so then what I want to do is I want to say, all right, when we do this, let's go ahead and move to just having this be based on the render width and the render height. And so we'll just reconstruct whatever that power of 2 would have been, right? So I'm just looking and saying, we're going to take the next closest power of 2. I don't remember what the actual index, that's what it is. And so now, in theory, we should be able to make this make some sense. Now, that doesn't look promising, to say the least, because I have no idea why we're so squat and weird for all of our lighting buffers, but we'll find out in a second. So let's take a look at what it decided to do for text width and text height, and why it didn't draw the whole thing. I wonder if one of our passes doesn't really center things properly. That may be the case. Yeah, let me take a quick look at that. So when we do depth peel to lighting, yeah, so the problem is depth peel to lighting needs to actually take the frag UVs now. That's, I think, the only thing that really needs to happen here. So instead of texel fetching, we need to actually do the bilinear to like downsample the results into the lighting buffer for processing. So yeah, in this case, we just need frag UV out. Like so. And then we can take frag UV in. And so then in that case, when we're taking these texel fetches, those texel fetches here would just instead be texture samples, right? So instead of texel fetch here, here, and here, they'll just be texture samples, and we won't do it that way. Now I believe I could make this actually be something that was switchable. So here's the alternate path where each of these is actually doing downsampling. Just blending together. Oh, wait. That's got a little overzealous. That's the path that I'm just going to preserve. Because just in case we wanted to not do that. Right? So this is going to be doing regular bilinear, assuming that bilinear is turned on for these. I don't remember if it is. But we'll find out in a second. Either that or it'll do nearest neighbor sampling, which is not really what we want, but we can always turn bilinear on. Let's go ahead and see if that's correct. Vert UV, that is true. We need a smooth, we need a in vert UV. Is it a V2 normally, I assume? Yeah. So let's see here. There we go. So now I think we're in better shape there, obviously. So let's take a look. Here is the game in its downsampled form, which is just using the closest power of 2, right? So here's a power of 2 version of the lighting. And you can actually already see that there's a little bit less of the problem we were having before, although it's still there. So as we go up the lighting scale, you can see sort of how that plays itself out, right? So what we want to do now is actually do some more intelligent things with the normal here. So there's the normal of where the light is coming from in these in this situation, right? And I think what we want to do is set that normal, the lighting normal, to be a little bit more sane. So that we can actually play with that a little bit. So, for example, I want something where the lighting actually is. I'd like to set the normal to point somewhere specific. So, for example, let's suppose that in the let's see here, compile Z bias program. Where are we at? Although now I think about it, maybe I don't care about that. Maybe it's just the flux that matters. Maybe it's just the direction that matters. So the place the light was coming from is really all that we care about. Yeah, so I guess here's what I'm sort of thinking, vaguely, right? So previously what we had, right, is we were taking the actual normals of all the surfaces themselves. and using that as something that we do in our lighting. Like, so, you know, if we look here, you can see like these are the resolutions. This is the normal information. And what I'm thinking is that what we might want to do instead of that is we might want to have the lighting be something where we're actually just flowing out the actual light itself, and the directional values are just based on where the light came from, not on what was there ever in the first place. So there would really be no normals anywhere else. It would just be, what would be in this buffer would just be the direction the light came from as it propagated, if that makes sense. Yeah. So as lights come together, their direction and their color would average together, right? So it would be very much like a light fluid, if that makes sense. And again, I'm just trying to figure out ways that I can make it so that this will work without the problem that we have, which is we don't really have a 3D enclosure we can really bounce the light around. Although I guess before I go down that route, we should, because we're sort of coming to the end of the stream here too, I should also say that there's a different thing we could consider doing, which is we could consider seeding the light path itself with completely separate information, which we could also do, right? Like we could have it so that we just send down all the reflectors in a separate pass, because we know what they all are, right? And that would mean that would be a slightly different situation, right? That would be one where we'd sort of just be doing vertex to vertex buffer processing, and we wouldn't really be doing much with respect to the incoming pixel values. So, for example, if you imagined us, because we're sending down, you know, like we're sending down like these cubes, right? And these sprites. We could instead just send down, when we send these down, we could just send down the plates themselves, these plates that we get. We could just record the plate information into the buffer directly. Meaning we wouldn't even really treat it so much like pixels. I know this is a little bit weird. I'm sort of thinking this on the fly. But if we wanted to implement the original algorithm a little more carefully and actually try to get it to work, you could imagine us saying, well, okay, when we have these plates coming in here, and we want to do the lighting versus, you know, the old school way of disk to disk transmittance, what we could do is just say, well, if we just recorded what all of these were, we don't have that many of them. We could actually do the algorithm a little bit more faithfully than it was originally, which is to say, we just build a vertex buffer of these things that gets traversed. Casey is thinking. For example, I'm just going to try to throw you a for instance here. So for instance, I said something like, okay, into the light buffers, what we're actually going to store here is they are literally going to be the tree of reflectors, and the reflectors are just going to be stored as the XYZ position of the reflector. Its radius, like how big it was, right? And then the emit front back and the normal. So basically we have exactly what we have now, but instead of writing into that buffer, instead of writing the anything based on the pixels, that buffer just gets written with reflector value, with actual like records of these reflectors, right? And so what we would need there is we need a spatially coherent way of stuffing the reflectors into the buffer, but that's really it, right? And then when we do that averaging up, we do the averaging just on the actual reflector information itself. That was sort of what I'd wanted to do originally. But we kind of stopped short of it. If we could do something like this, where it wasn't based on the pixels anymore, then we would have the ability to still bounce with the ceiling or a skylight or whatever else is in there, like either emit through a skylight or bounce off a ceiling. Which is more what I wanted. So the tricky part about it is really just the problem of not having any way of placing them into a pixel buffer in the first place. So that's why like the original algorithm had to do the weird like tree creation step, which, you know, is pretty janky. So I really wanted to avoid that if we could, and it would be nice to be able to do it in some other way, but I'm just not sure what that other way would be. If we, you know, we could use a compute shader which would have unordered writes, but that starts to get a little bit questionable as well. So I'm just trying to think if there's, I don't want to like totally abandon this particular way of doing things until I'm absolutely sure that there isn't some clever thing we could do here. And I'm just talking about some way of actually putting the reflector data in such that we wouldn't lose any of the ones we sent down just because they happen to be on the wrong side of like a plane like that. And to be honest, it does seem like this could work. I'm worried about the artifacts as you move through space. But it does seem like we could make that work. Like if you did just double down on it and say, okay, instead of using the depth PL pass, you just have one pass where you write directly into some kind of three-dimensional texture, which is not very deep. So, you know, it's maybe 16 high, but is fairly dense the other way. So, you know, it's like a 256 by 256 by 16 or something. If you did write the reflectors into that, then you could imagine downsampling that and running the procedure on it. And what that would look like is it would literally just average them the first time through. It would just average them in, right? So you just set the mode to additive. You run through, and what you write to the location is you just write to that location in the texel that is the point you're looking for. You just write the value of the reflector that's coming in, right? And so if you get more than one, they average together in an area. I kind of want to try that. I'm going to go to the Q&A, and here's what we're going to do. This is what I've decided. Because I kind of like this experimentation, right? And I feel like I want to give this a full try. So I want to like see if we can... I want to give this a full try before I say it needs to go. So I feel like what I want to do is just... because I can't quite figure out any way to get that ceiling in, I want to try one more time to get that to happen. So yeah, I think I might try it, but this week, I'm going to think about this over the course of the week and just decide whether I want to do it or not, but I think I'm leaning towards it. Trickster Zorua, I would like to ask something. Any advice for beginners? Most likely asked before, but I just heard about this, and while I'm interested in game programming, I never managed to learn a language. I don't have a lot of advice for that at the moment. This stream pretty much only focuses on people who already know how to program and wanted to see some game programming stuff, low-level game programming stuff. And I don't really have much in the way of pointers for like when people are very first starting. So yeah, I apologize for that. That is something that's pretty important, and I don't know that there's a lot of really great resources out there, but you know. SF Gartner, is there going to be a top level that doesn't have a ceiling and instead would have direct sunlight? Yes. But again, it would have a skylight, so we would still have a ceiling there, which are just emitters that are like in a flat plane emitting downward kind of a thing, right? So we would still have a ceiling at all times, more or less. CAD97, when you said does no library include no standard library, not quite yet. We did re-implement a couple of routines, and we don't use, like, for example, any standard library I/O. We don't use printf. We have our own printf and all that stuff. But there is like one or two standard library calls we are using right now: cosine and sine and square root. Because we haven't gotten to the point on the stream where I show how to do numerical approximations to those functions in SIMD. But eventually, yeah, no library does include the standard library. We almost don't use any of it now, and eventually we won't use any of it at all. And we don't use any other libraries. So I asked the kid, to do smooth edges, do you need to do the multi-sampling on all the buffers, normal, diffuse, etc.? So no, we don't really need that. And again, we're gonna have to make a pass after we get everything working to a certain degree to like take out any inefficiency that there is there at the moment. Because right now, we're probably doing a bunch of things we don't have to do. What I would like for the lighting is for it to be approximate and somewhat blurry lighting so that we don't have to have things like multi-sampling happening on the lighting. Right? So that'd be my hope. That's my hope anyway. Until it's all said and done, we don't really know. Kylo Pazestowicz, I don't know how to pronounce that, but any advice to working with all OOP and const programmers? Not really. You know, if you're not an OOP and const kind of person and you have to program with a lot of OOP and const programmers, it's not great. It's not a happy experience. So usually I just tell people to hang in there and find a better place to work at some point if you can. But there's not a lot you can do about that. The dogma in the C++ programming world is really strong and is not based on, you know, any kind of solid evidence. So there's not really a lot you can do. It's very hard to argue with people who have a particular dogmatic approach to programming that's you know, not based on any data, because you know it's close to a religion in that way. It's just based on people's beliefs and their feelings, and it's hard to argue with people about their feelings, right? So it's usually better just not to try, because you know, yeah, I mean, I don't know any other way to say it other than it's very hard to argue with someone else about their feelings. They feel like object-oriented programming is good, and so when you're arguing with them about using it, you're effectively arguing with them. It's like telling them, you know, that you shouldn't go to church on Sunday or something. It's like, if you believe a bunch of things that aren't based on any evidence you can go to try to look, you know, whether it's true or not, there's not a lot of ways that you can really have a constructive argument. So I try to discourage people from doing that if possible, and to just try to find programmers who program similar to you that you can work with. Eventually is usually the best way to go, just because you know, until there are really good hard metrics in programming that you can actually show people like, no, this is a bad idea, because you can actually measure its problematic effects, then really it's always just an emotional argument, and emotional arguments don't have any predictable resolution. You might convince somebody, or you might not, and you might just piss people off. Stephen Last, does GL have support for fully 3D textures? Yeah, sure. Textures in OpenGL can have a U, a V, and a W in the lookup. So if you want to, you can have, say, a 256 by 256 by 256 texture, and when you do a texel fetch, you can pass 3 parameters and fetch a texel, or you can pass a UVW and fetch a trilinear sample from one as well, if you want to blend them together. Reverix, as someone who was taught and always worked with OO programming, how does one enlighten themselves? Well, I guess what I would say is that the best way to sort of analyze any kind of programming is to see how much work you're doing to get the processor to do a particular thing, right? And you might say that the global metric for programming is for any given series of operations that the processor ends up doing, how much work was it for the programmer to produce the corresponding code in their language bug-free, or as close to bug-free as we know how to make it, right? Like, we analyze it and don't know of any bugs in it, right? So for a specific, and I guess I could say, for a specific bug-free set of CPU instructions, what is the code that produces that with the least effort on the part of the programmer, right? In the shortest amount of time. And the problem that I have with object-oriented programming is I've never found really any circumstances where it helps with that. And so a lot of the things that people say it helps with, they usually can't actually demonstrate that it did. They think that it does. I don't deny that they feel like it helped them. But I am unable to myself reproduce or have them show me how they were able to actually achieve that thing. And so that's usually the first step to looking past an ingrained opinion that object-oriented programming is awesome or effective, is going, can I produce real-world examples of how it was more efficient to write this code in object-oriented versus just writing the procedural version? And you may find that when you do that, you actually do find that object-oriented programming is better. And if you do, you should stick with it, right? I did not find that when I did that experiment. And I did it for a while. I was never really able to find an object-oriented paradigm that saved time consistently across real-world programming examples. It always was inferior to the procedural version. It involved more typing, more unnecessary structure to the program. It was less flexible because it typically involves more constraints. You end up having to do things like having these crazy things like friend and stuff in your language just to enable programmers to do things they would have ordinarily just been able to do in the procedural version. It changes the mental focus from the procedure, which is the thing that a CPU actually does, to an object, which is not something that really exists in a computer in any way, and so on and so forth, right? And so typically, I guess that's what I would say. And again, I'm not going to argue with you if you come to a different conclusion. Because like I said in the pre-stream, I don't know if you were here for that, I don't really like trying to force other people to program the way that I think is sensible to program. If they want to program in a different way, then they should program in a different way. And I also think that there's a lot of ways to program. Object-oriented is one of the few I've ever seen that I don't think is ever useful, so I don't really use it. But there's a lot of different ways you can program, and it's good to be versatile and be able to program, to think in terms of functional programming versus procedural programming, to think in terms of metaprogramming versus direct programming. All sorts of things can help you be an effective programmer. Object orientation is just one that I've never found useful. I just haven't been able to find the concepts behind it to really come together to produce effective programs in a more efficient way than the procedural version. Emma Krantz, could you overlay an additive gradient on top of the car geometry to make them seem to have more depth to emulate more of a cone shape? You could do a bunch of things. If you want to go all out, you could actually have depth maps or normal maps for the sprites. So I guess what I'd say is, you've got a lot of options there. You can definitely cheat and just map a sphere or a cube, or not a cube, a cylinder, to get more variance to the reflection across the surface. And depending on how close the geometry of the underlying thing that got drawn evinces that, you will get better and worse results. The full-on way to do it is to actually have the art path have normal maps in it, because then it's exact in a sense. But that depends on whether you have access to artists who can do that or want to spend the time. And Cuber Caleb said, wouldn't trilinear sampling for a 2D texture imply sampling across different MIP levels? If so, what t-value does the GPU use to interpolate between the layers? So first of all, your hypothesis is correct. Trilinear sampling for a 2D texture does imply sampling across different MIP levels. And in terms of what the t-value is, it's based on the texture gradient that is seen. So what generally happens is, I'll try to explain this. So if you imagine here is the pixel grid, then you can imagine if I'm talking about how to pick a MIP level. Well, if I was to say that I'm going to talk about texels that happen to line up so that the distance between one texel center, let's say this is a texel here, it happens to be off center, but who cares? The distance between one texel sample, let's say this, and the next one is exactly the same width as the pixel grid that it is rendering to, then you might say that it's 1-to-1 in terms of size, right? And at that point, the MIP level is plainly 0, because the thing that we're drawing is the same size in texels as the screen is in pixels. The texel size and the pixel size are the same. So we don't need to subsample it. Now let's say instead we had something that looked more like this. So now you can see that I've got my texels are 1/4 of the size, right? So here's texel A before. Now we have texel A is here, and here's B and C and D, right? Well, now we're basically saying it's 2-to-1 in both directions, right? Because the width is half, the width of a texel on the screen is half a pixel. So optimally, what we'd like to do there is we'd like to sample from MIP level 1, right? Because we'd like everything to have been averaged down by 1, so that now we're back to having A, B, C, and D merged together into another texel, we'll call that E, right? Which is A plus B plus C plus D divided by 4, right? Or some other way of computing a MIP level. So that when we sample it, we are sampling properly the average of all of these, which again is important because since we're going to take a bilinear sample, since this is off-center, our bilinear sample wants to average the averages, right? So that's why we have the MIP, so that we can take into account everything that would have been in that subsection. So then you might ask yourself, well, what happens in between? So what happens if the actual distance between them is like some odd number? So here would have been exactly 1-to-1, and here would have been 1-to-2. What happens when we're in between? Well, that's your t-value for trilinear. So however much the width is between half and whole, that's what you get. So typically the MIP level, if you think about it, the LOD level is actually a continuous value. 0 means 1 to 1, 1 means 1 to 2, or however you want to think about this, right? Along any dimension. And what you get when you do this is an actual continuous value. You might end up with like 0.75 or 0.53 or who knows what, right? And that's how far in between the two MIP maps you would be. And furthermore, as you go up and up and up, if it's like 1.27, then we're part of the way in between MIPS 1 and 2, and so on. Now, this also, if you haven't ever looked at this before, this is also, if you want to understand anisotropic filtering, you can see why anisotropic filtering becomes important, because you don't know that these values are the same in either dimension, right? So it could be that my thing is very long and skinny, and so that I'm at a very high MIP level this way, but a very low MIP level this way, right? And so anisotropic filtering, or things that take more than one tap down the MIP chain or do other things like this, are ways of trying to reconstruct what the value should be, given that you don't have the right set of MIP maps for every occasion, right? Ideally, you would have the MIPs, every permutation of MIP. So if you imagine that you had, let's say a 256 by 256 texture, well, that's 2 to the 8th, right, by 2 to the 8th. So really, we should have like 8 LOD levels there, okay? And when we make a MIP chain, that's how many we have. But what if we wanted to sample from a MIP that was really all the way in X, still there, it still had its full width, but was not that wide in Y, right? So we shrunk the thing down because, like we're shrinking it this way, but not shrinking it this way or something, or vice versa. In this case, we're shrinking the Y down and leaving the X wide, right? Well, if we do that, we really need a MIP level that didn't get shrunk in Y and that did get shrunk. Didn't get shrunk in X, but did get shrunk in Y, and we don't have that in a standard MIP chain. So if you were going to produce all the MIPs you would actually need for pre-computed for sampling, what you'd actually have to do is, instead of having 8 MIPs for this, right, you'd actually have to have 64 MIPs. You'd have to have every X level have every Y level in it. So you'd have a 2.8 by 2 by 2, and a 2.8 by 2 by 3, and a 2.2 by 2.8, and a 2, blah, 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 blah. And then you would sample based on the gradients for both X and Y into the correct MIP, right? And by the way, if you had a small number of these, and you wanted to do this, you could. So if you wanted to do really good downsampling, you could produce a number of MIP maps, far more than 8 for a 256 by 256, that are all based on giving you fast ways to do good sampling at arbitrary different angles and stretches, right? I think I'm basically out of time, but let me just double check what we have, if any more questions. What are your opinions on DRM? I'm against it. Let's see. I'm working on an AI to play a game, and I'm wondering if you have any general tips for it. More specifically, the game is World of Warcraft. Right now, I'm only at basic functions and working on an image processing pipeline. No, I don't really. I'm not really an AI programmer. I don't spend any time doing much of that, so I don't have much in the way of bot advice. I've never even written a bot for anything. It's not something that's ever appealed to me for some reason. All right, let's wind it down here. All right, thank you everyone for joining me for the episode of Handmade Hero. It's been a pleasure coding with you as always. If you would like to follow along with the series at home, you can always pre-order the game. It comes with the source code so you can play around with it yourself. We also have a forum site you can go to if you want to ask questions. about what we've done in the series. We have a Patreon page if you want to support us and the videos. We have a schedule bot you can use to find out when we're going to be live if you want to join us live, and an episode guide you can use if you want to catch up on old episodes that may have covered something you're interested in. There's also a great search feature that was implemented by the community that's really pretty darn cool, so you can quickly find the episodes you're looking for. That's about it for today. I will be back, I think, next week. I might take some time off coming up here. I'm not sure. There may be a summer vacation on Handmade Hero, so I'll keep you posted on that as it goes. Definitely always look at the schedule bot to find out, but I think I'll be back next weekend for playing around with the lighting a little bit more. Until then, have fun programming, and I will see y'all on the internet. Take it easy, everybody.